Now we're ready to analyze our data. The table shows the crack width produced from hitting material A and material B with different forces. Notice how the units are given at the top of each column. We'll want to be sure to include those units on our axis labels. Our first step is to determine what is the dependent variable and what is the independent variable. An independent variable isn't changed by other variables you are trying to measure. Time is the most common independent variable. A dependent variable is something that depends on other factors. For example, the score I get on my test depends on the number of hours I study. Score is the dependent variable, and hours is the independent variable. Now let's look at our example. Ask yourself, the blank depends on the blank. Well, I can see that the crack width depends on the force used. This means that our independent variable is the force and our dependent variable is the crack width. Don't be fooled by the table because it has 3 columns. Remember that force is our independent variable and crack width is our dependent variable. Our table, though, is just combining 2 sets of data. So we're going to have one where the independent variable is force and the dependent variable is crack width and material A. And I've pulled that out just to make it clear that that is one set of data. And the second set of data will be the force in its relationship with the crack width and material B. And you can see I've also pulled that out into a separate table just to make you realize that really we're using 2 sets of data in one table, but both of them share that independent variable of force. Next, we want to ask, what is the biggest value and the smallest value for the independent variable? This will help us decide on our scale for our line graph. We can see that our smallest value is 10 and our largest is 68. And next, we want the biggest value and the smallest value of the dependent variable. Since we're going to be doing these on the same graph, we want to consider both dependent variables. So what is our smallest dependent variable on both columns? Well, our smallest one would be 0.025, and our largest one would be 0.562. These values will help us to determine the scale used on the y-axis. I've recombined my table into one because that's more than likely how you'll see it in your lab and your projects. How do we make points? Well, we have to establish a relationship between the independent variable and the dependent variable, and this creates an ordered pair. So for example, our first set of points describe the relationship of the force and the crack width in material A. We call this first number the x-coordinate, and the x-coordinate is describing the force used. The next number is called the y-coordinate, and it describes the crack width. I'm using the crack width set for material A for my first set of points. So when I have 10 newtons of force used, I produce a crack width of 0.05 millimeters. This makes an ordered pair. Similarly, if I had 68 newtons of force, it would produce a crack width of 0.562. So now I have 6 ordered pairs for material A that I can graph. Let's do the same thing for material B. This time, my independent variable is still going to be force. So my ordered pairs will still all start with the same x-coordinate. However, my y-coordinates will be taken from the dependent variable crack width and material B. So I'm going to use these data points for my y-coordinates. This gives me 6 more ordered pairs, 6 more points that I can graph. Remember, though, that these points will produce a separate line from these points. There are 2 separate lines on my line graph. Now we can build our line graph. The first thing I'm going to do is put my title on to describe what I am going to be showing. Notice the title of my graph is not just graph. Instead, I use it to describe what I'm going to see. Crack width developed by impact force on material A and B. My next step is to draw my x-axis, which is a horizontal line, and my y-axis, which is a vertical line. Now notice that where they intersect is at 0. We call this the origin, and the order of period here would be 0, 0. All my x values that get bigger as I go right, and all my x values get smaller as I go left. My y values get larger and more positive as I go up, and my y values become more and more negative as I go down. All my values for my x coordinates are positive, and all my values for my y coordinates are positive. This tells me that I'm only going to need to use this part of the Cartesian coordinate system. Quadrant 1 describes points that have a positive x coordinate and a positive y coordinate. So I line up my straight edge horizontally, and I draw a straight line. This will be my x-axis. Now I'm going to turn my straight edge so that it's vertical, and I'm going to draw a vertical line. This is going to be my y-axis. Now I need to label each axis. My x-axis shows the force used in newtons. And I make sure that I put the units along my axis too. My y-axis describes the crack width in millimeters. Notice that I don't mention whether it's with material A or with material B, because if those will be described by using different lines, and we can make a legend. Now comes the tricky part. We want to define the scale on each of the axes. So first I'm going to start with force. We said earlier that the smallest was 10 and the greatest was 68. I counted the number of boxes across my graph, and my graphing paper only has 40 boxes. So I can't make it 1 unit equals 1 Newton, because I would only be able to graph 10 through 40. Anything larger than 40 would be off my graph. So instead, I decide to make each box worth 2 newtons. I labeled my axis so that I can find the points easily. So notice I went ahead and just labeled every 4 with a number so I can find them easily. Now, when I have a 68 for my x coordinate, I'll have a place to graph it. Now let's look at my y coordinate. It's a little trickier. So we said the smallest was 0.025 and the largest was 5.562. I'm going to give you a hint about how I do these. I make sure, first of all, that they have the same number of digits behind the decimal, which they do in this case. But for the other ones that don't, go ahead and make sure that you have the same number of digits behind the decimal. And now, think about what you're comparing. You're comparing thousandths. So if I have 0.025, that could be written as 25 over 1,000. An easy way to remember this is you put a 1 underneath the decimal and then a 0 under each digit that's to the right of the decimal. That's an easy way to convert a decimal to a fraction. So I can think of it this way. If I'm going to make these be thousandths, then I'm going from 25 to 562. So that will help me visualize this a little better. Let's count how many blocks I have vertically on my graph. I have 30 blocks going this direction, vertically. I want to be able to plot all of my data in here. And I want to spread it out as much as possible so that I can see what's happening. In other words, I don't want to do this. I don't want to make each of these be a tenth, because if I do that, all of my data will be squeezed in this little region. Instead, I want to use my whole graph as possible, if possible. So I start thinking about, well, if I have to cover 562 over 30 blocks, what would that be? That'd be 18.7, but that would be a really, really wonky unit for my intervals to be at. Instead, why don't we try to make each of them be something more like 0.02? I labeled my vertical scale. Notice each box is 0.02. Now we have our graph ready to plot our ordered pairs.